Access Reality. I'm Ali Kadelia. I have here Dr. Michael Huemer, who's a professor of philosophy at the University of Colorado, and his book is entitled Approaching Infinity, which addresses 17 paradoxes in infinity, most of which have yet to be resolved. So thank you very much for being here, Dr. Huemer.
Yes, thank you for having me.
Perfect. So, so your specialty is philosophy, is that correct?
Yes, that's right.
All right. And I don't think, I think most people outside of academia don't, they really think of philosophy and mathematics as being fields that are totally separate and have nothing to do with each other. Don't really appreciate how much philosophy is in mathematics and how important mathematics is in solving philosophical problems. You're immersed in this, so, but are you often surprised by how separate people think these two fields are?
Well, I guess I'm not really surprised. But yeah, there are a lot of kind of connections. There are mathematical applications to philosophy and vice versa. Probably mathematics is more useful for philosophy than the other way around. So, mathematicians really don't use very much philosophy. And if you do, then you're kind of a weird mathematician, like the intuitionist or something. But philosophers use a fair amount of mathematics. So there's a fair amount of probability theory used in epistemology. And of course, formal logic and, other things like that.
Yeah, so how much mathematics do you have to know as a philosopher, specializing in philosophy of mathematics?
Yeah, it depends on what you're doing, right? Yeah, so if you're doing philosophy of mathematics, then you should be pretty good about mathematics. I mean, a lot of the issues, so, we debate kind of ontological issues like, do numbers really exist? And what are they? And there's kind of some epistemological issues like, how do we know mathematical facts? So, those issues don't depend upon kind of details of mathematical systems, right? Just sort of like general epistemological and metaphysical issues.
Yeah. So,
right, but if you were doing epistemology, then you really have to know probability theory. And in this case, if you're kind of theorizing about the infinite, then you definitely do need to know the mathematical theories, especially Cantor's theory about the infinite and his view about numbers.
Okay, so you're a philosopher who wrote a book about infinity, which one can argue is a mathematical concept. How would a mathematician writing a book about infinity would have differed from what you wrote?
There would be a lot more math, and there would be,
so it'll be a lot more boring. It'll be a lot more dry.
There'd be, a lot of symbols, and then there would be proofs of things, right? Okay, so, actually Georg Cantor is a very interesting mathematician because he's a lot more philosophical than most. So, if you look at his book, in which he sort of introduced this theory about transfinite numbers, it's kind of philosophical, right? There's kind of like a discussion of the nature of sets, basically, and like his view about what numbers are. Which is kind of understood in terms of sets. And then from that, you get the idea that infinity be a number. Whether there are infinite numbers is kind of a philosophical question, right? Now, this comes to be widely accepted by mathematicians that there are infinite numbers and they're genuinely numbers and not some different kind of thing. And it was accepted pretty much because they accepted Cantor's arguments, right? But then like an ordinary mathematician, they would just spend time proving things like just assuming that there are infinite numbers. Take that kind of philosophical point for granted. And then they would just prove things about how this infinite number is different from the other infinite number and so on.
I was going to say the great mathematical problems, when mathematicians are trying to devise proofs for those, do they not rely on philosophy to help them as to how to go about that problem, let's say?
I would like to say yes, but probably not. That is, philosophy probably doesn't help very much if you're trying to prove something. Sometimes you might kind of hurts you, because like if you have certain philosophical views, then you have to not use certain kinds of proofs. Okay, so like the intuitionists in mathematics, they don't allow reductio ad absurdum as a method of proof, which really restricts you. And it's kind of for philosophical reasons they don't allow that, and sort of like don't allow using the law of excluded middle or things like that.
Yeah. Now, going into the subject of your book, so infinity is really somewhat of a puzzling topic, because it doesn't really come intuitively to the human mind, because it's not something we deal with in the physical world. We deal with 4 of this or 10 of that. We never see or touch anything that's infinite in number. Um, so,
Yeah.
how is that kind of why the reason that got you interested in it and writing about it?
I mean, I'm not sure that's exactly true. So, there's space around you all the time, and that's kind of infinite, right? It's not only infinitely extended, but infinitely divisible. You might say you don't see the infinite divisibility because there's a limit to how small of an object you can see. Um, but so like you see the thing that we believe contains sort of infinity in it. And then we think about numbers, and of course you don't see numbers, but sort of they're pretty familiar. And you think however large a number is, there's always that number plus 1. So sort of like the notion of the infinite is in kind of a common understanding. It made me want to write about it was basically all of these paradoxes. It was that there are all these scenarios that people have come up with where some bizarre thing happens, or even the contradictory thing, and a bunch of them involves being infinite. Then you get some weird results. And I wanted to just figure out what's going on. There were a number of years when I would tell students about these paradoxes, but I didn't have any solution.
All right, so we'll get back to the paradoxes that the book was based on, but um, in the way that 4 is a number or 5 is a number, is infinity a number, or is it just a concept of there's more and more and more? Or is
Well,
it like is it do you think it is in reality a discrete number that we just can't pinpoint yet?
so I think it's not a number. I wouldn't say it's a concept either, right? So the concept of infinity is a concept, but infinity isn't a concept, right? Just like the concept of the number 2 is a concept. Okay. Well, it's kind of an abstract object, but the regular numbers are also abstract. So, but okay, why is it not a number? Because as I think about it, a number is a determinate quantity. And infinity, so the concept of infinity is a quantitative concept. It's not the concept of a specific determinate quantity. So think about like how a lot is a quantitative concept, but it doesn't refer to a specific determinate amount. Now, infinite means something like exceeds any assigned value, something like that. So there are infinitely many numbers. What that means is you can have arbitrarily large sets of numbers, right? Like take any collection of numbers, there exists one that's larger than that. And that's basically what it means, that there are infinitely many. It's not assigning a specific quantity set of numbers. It's saying that it exceeds all specific quantities.
Okay. So that sounds pretty clear that you feel that infinity is not a number. I agree with you. Does the idea of infinity then help in any way prove that numbers exist independent of our minds, that they exist out in the real world? Because we can't conceive of infinity, but we accept that it's there. So then the same can apply to the numbers.
Yeah, I mean, that would be kind of a weird way of arguing, because the natural numbers are less controversial than infinity to begin with, right? So like if somebody's accepting infinity, they're accepting the natural numbers too. why I believe that numbers exist is so like this is two fingers, and there are examples of things that are two. Like here's two hands. So I believe that two exists in the same way that I believe other properties exist. It's like blue exists because I can observe some blue things, and there's something that they have in common. So what they have in common is blue, the property. So similarly, like what this situation has in common with this situation is two-ness, right? The property of being two.
But you would concede that two exists in a different way than your two fingers exist, because the two fingers are in this physical world, whereas just the number, the property of the number, kind of is a construct that we use to organize the physical world around us.
Well, does it exist in a different way? That's a little bit of a confusing idea, right? Are there different ways of existing? But it's definitely a different kind of thing, right? It's not a concrete particular, but so two is a property, like the way blue is a property and being square is a property, and so on. It's just that this particular property requires two subjects for it to be instantiated. Most properties can be instantiated by a single object, but two-ness has to be instantiated by two objects. But yeah, so it's not a concrete object, but it's also not, I wouldn't say that it's a construct. Like it's not dependent on our minds. So like there's a fact about how many planets there were, how many planets there are, and that was the case before there were any people. Like there were 8 planets before there were any people. They weren't called planets and they weren't called 8 at the time, but the property that they currently instantiate, they instantiated before people existed.
Okay, so that comes to the wider kind of question of whether mathematics exists in the real world or is it just in our minds. So you seem to be indicating that it exists objectively and independently, but maybe what we call them in the language we use to denote that is maybe ours.
Yeah. So, I guess I'm a Platonist. So like, I think these mathematical objects exist. Not every mathematical object that people think exists, I think exists. So like, I don't really think imaginary numbers exist. But basically, I think if it's possible for it to be instantiated, then there is a real mathematical object. So, it's like, it's not concrete, but it's a thing that has properties that you can talk about, and like you can, prove things about it, you can correct incorrect beliefs about it. And, it's not dependent on our mind. Like we didn't create the numbers because there were numbers of things before we were around. I think similarly about geometrical properties. They were shapes and they had characteristics before there were people and so on.
Okay. Now, the fact that infinity kind of exceeds every number that we could ever think of, could infinity be thought of as an idea that kind of is the anti-property of numbers, or that negates the property of numbers? Because it's the opposite of a definitive quantified property.
Yeah, what you might be getting at is it's more of a negative concept than a positive concept, right?
Mm-hmm.
Actually, this view is the opposite of Descartes' view, right? Descartes' view was you understand the finite at the negation of the infinite. And my view is the opposite, right? You understand particular finite numbers like real numbers and natural numbers. And the idea of the infinite has to be defined in terms of that in a negative way. Like no number is large enough, right? Like how large is space? Well, like there's no real number that's large enough to capture all of it. Rather, for any region of space exists a larger one. But yeah, so negative concept in the sense that it's like the absence of limits.
So you just mentioned larger than space. So, I would say that in probably the average person's mind, when they think of infinity, they're thinking of size, like as the example that you just mentioned. Basically, something infinite means that it's infinitely large. Wouldn't you agree that infinity, though, in reality is a property that's unique from size. And as evidence for that, you have, groups of infinities, some are larger than others. So it's some distinct property, infinity that is really independent of size per se, as we perceive it.
Well, so, I mean, infinity isn't a particular size, but it's not like it has nothing to do with size, right? So like, if you have something that's infinite and then you have something that's 1 liter in volume, the infinite thing is larger. So it's got something to do with size, but it's not a specific size. I think I forgot what I was going to say about that.
We're talking about infinities, some infinities larger than other infinities.
Oh yeah, yeah. I wanted to comment on that. I mean, so yeah, the standard view on finite mathematics due to Cantor, there are infinities of different sizes. Now, I don't think that that's literally true. I don't think that there are larger and smaller infinities. And it's not that I'm rejecting Cantor's mathematical proofs. Like, I think his proofs prove something. They don't prove that there are different sizes of infinities. And the reason for that is, well, like, okay, there aren't infinite numbers, as discussed previously. So like the greater than relation doesn't really apply. There is this relation of, you can put one set into a one-to-one correspondence with another or not, right? Like, so there are facts about that. I just don't think that that adds up to one of them being literally larger than another in the same sense that 4 is larger than 3 or something. So, like the set theorists and, number theorists traditionally say that there is the same greater than relation. Okay, but the thing is that central intuitions about the greater than relation that apply to natural numbers do not all apply when you're talking about infinities. Okay, so like I think this is a central intuition. If you have a determinate quantity and you add something to it, the result is larger. And that is, if you believe in infinite numbers, you have to say that they do not satisfy that. You can pick an infinite number, you can add to it, and then the result is not larger. It could be the same size. And so, right, so, but I think that that just shows that the intuitive notion of greater than doesn't apply to infinite collections.
I mean, mainly some of the things I think of when I try to grapple with that is, for example, if you look at the group of odd numbers, that goes to infinity, and whereas a group of all numbers, it's also an infinity, but it has more in it. So that's kind of like where I was coming from with this.
Yeah, I mean, well, you might think, like, there are these two arguments, right? Actually, it'd be easy if I change it to the even numbers. So are there more natural numbers or are there more even natural numbers? You go, well, there's got more natural numbers because the natural numbers include the even numbers plus the odd numbers. And there's the counter argument, no, there must be just as many even numbers as natural numbers because, like the even numbers can be thought of as the natural numbers times 2, right? For every natural number, there's that number times 2. So there's at least one even number corresponds to it, right? So like you can give these conflicting arguments. The traditional view in mathematics since Cantor, like this wasn't the traditional view before Cantor, but since him, the traditional view is to just accept the second argument and say there are the same number of even numbers as our natural numbers. And then just ignore the other argument, right? Just ignore the fact that the even numbers are a proper subset, right? And like, we just reject that criterion, right? So like my view is no, both of those arguments are completely compelling with the ordinary notion of greater than. That proves that the ordinary notion of greater than does not apply to infinite collections.
Okay.
Right?
Now,
by the way, that was. So I was going to say, by the way, that was Galileo's view, right? Like the thing that Cantor discovered, like Galileo figured that out before, that you have these, two infinite sets where there could be these two conflicting arguments. Galileo drew the correct conclusion that means that greater than and less than don't apply to infinite collections.
Yeah. So another thing is if infinity is a property, are there certain types of things it can be ascribed to or it can describe, and things that it can't apply to?
Um, yes. So, like there are infinitely many. So there are collections that infinitude applies to. Space, I think, is infinite, infinitely extended, and it's also infinitely divisible, and time also infinite. Um, there might be an infinite amount of matter in the universe. Don't really know. Um, so, in the book, I try to figure out what kinds of infinities can really exist and what kinds cannot. So my central claim about that is you cannot have an infinite intensive magnitude. You can have an infinite extensive magnitude. So an example of that is the extension of space, like it's infinitely extended forever. Um, but an example of an infinite magnitude might be temperature. So like there cannot be infinite temperature at a particular location. Um, there can be like infinite energy distributed across an infinite amount of space, but it can't be infinite energy in a finite space because that would give you an infinite density, which is an intensive magnitude. There can be infinite collections of things, like a collection that's infinitely numerous also, like there are infinitely many natural numbers and so on.
Now, did you say that space is infinite?
Yeah, I think it's infinite.
Okay. Now, if space is expanding or constantly expanding, um, then like if it was already infinite, how can it be expanding further?
Yeah, yeah. Well, yeah, you might think, oh, so expanding means it gets bigger than it is, but it's going to be the same size because it's still infinite. Or it will have the same non-size, right? Because, if the infinite isn't a size, then it'll continue to not have it. I mean, what the physicists mean is something like each local region is expanding. Right? So that, yeah, like, so there's, just take this finite region, it expands. And then the same thing happens with the region next to it, like all everywhere. They're all expanding.
Hmm. But the sum of those, I mean, still would be infinite, right?
Yeah.
Some of
Yeah,
those
see, like,
regions.
yeah. And I mean, this is a good point to bring up again. Like, when I say that space is infinite, I do not mean that space has a particular size and the name of that size is infinity. That's not it. Right? What I mean is, take any size, exists a region that's larger than that. Right? Where the sizes that you're allowed to take are all finite, real number values.
So you're saying that the size isn't expanding then of space? If
There's
it's
no
already
size,
infinite?
there's no size of all of space. Like
I see.
space as a whole, the infinite object, it doesn't have a size because that would require a determinate quantity. It exceeds all particular sizes.
Okay. And another example you brought up was the infinity of time. And we think of time as, from our present standpoint, future and past. And
Yeah.
isn't time finite, though, when you go back in the past, if it started at a certain point at the Big Bang, according to physics? So how can it be infinite then?
Yeah, well, I mean, almost everyone thinks that it's infinite in the future, which is enough to have an example of infinitude. Is it infinite in the past? I mean, so there's a conventional view, like that. I think the conventional Big Bang theory is that space and time started with the Big Bang. There's no time before that, but I just disagree with that. Um, by the way, so like, I'm going to mention what Roger Penrose says about this, right? Which is, so in the conventional Big Bang theory, there was a very large quantity of mass energy in a very tiny region expanding outward. And that was just the first thing that ever happened for no reason, right? Just at the first moment of time, that's how the world was. Okay, and Penrose did this calculation that says, well, the probability of that being the initial state of the universe, if you like picked a random initial state, is something like 1 in 10 to the 10 to the 124 power. So like, I think like this is not really a satisfactory theory, right? Like it was just like that for no reason, with no cause. It just started out in this incredibly improbable state. And if you're going to say things like that, I think actually a better theory is that the universe came into existence in the year 1950 in the state that it was actually in. It's like you could hypothesize that, right? The state that in 1950, maybe that was the first thing that ever happened, then it continued from there. Right? And that is actually more probable.
So
like
your contention, your contention is we don't know enough to say that time actually started at the Big Bang. Is that what you're saying?
I mean, I'm saying something stronger. Like I think this is a highly implausible theory.
I see.
Right? Like, you know, I think time is infinite into the past. It's hard to conceive of the beginning of time. Right? So if you think about when you think that you're imagining the beginning of time, you're probably imagining something incoherent. Right? So if you imagine time coming into existence, that's incoherent. Because like what you're imagining is first, there's no time, and there's time. What that means is there's a time when there's no time, followed by a time when there is time. Okay, that's incoherent. There can't be a time when there's no time. Right. Now, I mean, you don't have to contradict yourself. Like, you know, you can describe a coherent mathematical structure, but it's just that when you try to imagine time beginning, like it's almost inevitable that you imagine this incoherent thing. Sort of like when you imagine the edge of space, and then you think like there's this barrier here, and then what's on the other side of the edge of space? And then if you imagine like there's this blank place over here where there's no space, okay, that's incoherent, right? You know, most people accept that the edge of space is impossible. It's not mathematically inconsistent. Like there could be a consistent mathematical structure where there's a limited amount of space, and it's not circular. But it's just that, you know, when you think about it, it just doesn't seem like space could be that way. And most people agree with that. So, you know, use that as an analogy to how I think that there couldn't be a beginning of time. Right? Like even though there's a coherent mathematical structure, when you try to conceive of it, it sort of seems inconceivable.
Is the solution to that then to say, as you've offered, either that that's not true, time is infinite in the past and physics just hasn't caught up with an explanation yet? Or could the other possibility be that our minds are too limited to understand a time without time, so to speak? Like, notice the language I'm using. I even use the word time.
Yeah. Yeah, I don't like conclusions that go, oh, we're too limited to understand how P, where P is something that seems incoherent, right? Like, if you're saying that, you should just say not P. So, I mean, my view is, yeah, no, the view about the Big Bang is false. Probably time is infinite. I don't know that. I don't know that the past is infinite, but I kind of think it is. There are some theories in cosmology that have infinite past time, right? So like, you know, it's not, I'm not going against everyone, right? So as I mentioned, Roger Penrose, he has this cyclical model where time extends infinitely in both directions and the universe just goes through these infinite cycles.
Is it plausible that someone can come up with mathematical proof that time is infinite in the past?
I don't think so. I mean, there couldn't be a purely mathematical proof, right? There have to be substantive metaphysical premises. All right, and I say that because, well, there's a consistent mathematical structure, right? So like take the structure of the positive real numbers. I think that's a consistent mathematical structure, right? So like it could be proved that time doesn't have that structure without some substantive metaphysical premises, right? Like, you know, for it to be a mathematical proof, it would have to be like a consistent structure.
Well, it would have to be consistent with the laws of physics as we know them today, but not necessarily consistent with theories that are derived from those laws, like the Big Bang Theory.
Yeah, well, I mean, you know, we might be wrong about the laws. Right?
Oh,
so
that's a deeper layer of philosophy than I was prepared to go into.
Well,
being wrong about the laws of physics. Yeah.
Yeah. Well, I mean, actually, it's pretty plausible, right? Because if you think about like, you know, the history of the human species, we always were wrong. We always were wrong about what the laws were or whatever. And like, you know, I mean, it's a little bit weird to say, okay, the time that you are alive happens to be the first time when we got it all correct, right? And like, you happen to be living at the end.
Of our understanding, yeah.
Yeah.
Yeah. Now back to the question of, you said infinity is a property that can use to describe some things and not others, right? Can you tell us how one, like examples of things that cannot be, like what are the criteria by which, okay, now you can describe this with infinity versus not?
Well, I mean, you know, some things are finite. So like you're finite.
But
Right?
in infinity of finite things. For example, you know, one human versus infinite humans. We know that doesn't actually exist, but it's theoretically possible. Or is it?
Yeah. I mean, there could be an infinite number of people. Okay, right? For uninteresting reasons, the people who are not on Earth might not count as humans. Okay, so maybe there could only be finitely many humans, but there could be infinitely many persons, including ones that look just like us. Like I don't know that that's the case.
But yeah, what I was trying to get at is there may not be an infinite number of humans, but it is still appropriate to describe humans with the property of infinity because theoretically it could be possible. It doesn't exist now, but you could like, or is it? Or maybe it's not possible to have an infinite number of pens or cars.
I mean, as far as I know, it is possible. So, like, I have a theory about when infinities are impossible, and it allows for there to be an infinite number of material objects. So, like, my theory is the impossible infinite is an infinite intensive magnitude. So, you don't have to have that in order to have an infinite number of pens. These pens would have to be, of course, distributed through an infinitely large space. But, you know, since space is infinite, okay. It's like outside the range of what our telescopes can see, there may be more stuff. There may be sort of like parallel universes that are too far away to see. And then, you know, and there's more people there and more pens or whatever. And like, there could be an infinite number of them.
So according to your theory then, what distinguishes possible from impossible infinities? Is there like a set of criteria or?
Yeah, so I mean, I guess I'm going to say more about this thing about the intensive magnitude. Quantities could be distinguished into cardinal numbers and magnitudes. So cardinal numbers are like the counting numbers, like 1, 2, 3, and so on, and maybe 0. And then magnitudes are usually represented with real numbers. So that includes the length of an object, or the temperature of an object, et cetera. Okay, extensive magnitudes are basically magnitudes that are additive across the parts of a thing. So like if you have an object, so length is extensive. If you have an object with a length, the left half, the length of the left half plus the length of the right half will equal the length of the whole, you know, as long as you take non-overlapping parts. Okay, but there are these other magnitudes that are not additive. Like if you have a cup of coffee, the temperature of the left half plus the temperature of the right half does not equal the temperature of the whole, right? Okay, so those are the intensive magnitudes, right? So my claim is you can't have an infinite intensive magnitude. Like you couldn't have infinite temperature or infinite energy density. And the reason for this is the explanation that I give of what infinitude means in the other cases cannot be given for intensive magnitudes. So like what it means that have an infinite number of things. So what it means is that you have a set with arbitrarily large subsets. Like there are infinitely many people means the set of people have, for any number n, the set of people has a subset that contains at least n, right? Or contains more than n members. And then, you know, for extensive magnitudes, what it means is there are arbitrarily large parts. So space is infinitely expanded means take any given volume, but these have to be real number volumes. There exists a region of space that's larger than it. Okay, but then you cannot say this about intensive magnitudes. So somebody said there's an infinite temperature. You can't explain that as saying there are arbitrarily large subsets, and you can't explain it by saying there are arbitrarily large parts. Because because it's not additive across the parts. So like you don't get the infinite temperature by taking different parts, with finite temperatures. Okay, so then to explain the infinite intensive magnitude, you basically just have to have an infinite quantity. Is you have to posit a number that's larger than all the real numbers, which I say is impossible.
So back to the inspiration for your book, would you say that Zeno's paradox was the prime motivation behind writing the book?
But that was one of the paradoxes. Yeah, I mean, there are several paradoxes. There's there's like 17 paradoxes of the infinite. So, one of them being Zeno. Although I didn't think Zeno's paradox was that hard, right? Like it's might be the most famous paradox of the infinite, but it's not the hardest. It's not the most mind-boggling.
Yeah. So just tell me if my understanding of it is correct. Is that you have a distance between point A and point B, and there's an infinite number of points from point A to point B. So how can you, with finite motion and distance, kind of cover that infinite number of distances? So that's the paradox. But we do know that you can go from point A to point B in the real world.
Yeah.
Now, calculus kind of solves this by saying that, a finite line will have infinite number of points in there. And is the traditional view, the mainstream view, is that this has been solved by calculus?
I think that's the mainstream view, but that's also false. So so first, what the puzzle is. I mean, the puzzle is about infinite divisibility, which is not exactly the same as saying there are infinitely many points, because roughly speaking, some people think that there aren't any points. Points don't exist, but space is still infinite. Space is infinitely divisible. In fact, I think that's a pretty reasonable view. That might be true. So like, and this is like a digression, but this is my problem with points. Okay, what is the point? It's supposed to be a part of space, but how big is it? The answer is it's of size 0. Okay, I think there cannot be a size 0 object. It can't be a size 0 part of space. And like the reason for this is 0 means not any. Like having 0 of something is not having any of it. It's not having a really tiny amount. So like having 0 volume is having no space. Okay, so the volume of something is the amount of space that it takes up, or the amount of space it constitutes. So having 0 volume means not consisting of space and not constituting any space. And there can't be a part of space that does not consist of any space at all. So anyway, leave that aside. So the problem is infinite divisibility. You can go, so you're trying to go from point A to point B. You first have to go half the distance, and then after that you have to go half the remaining distance. Then you have to go half the remaining distance, and so on. This is all okay, even if there aren't any points, because all of these distances are still, they're not point size. They're still of real size.
They're measurable distances.
Yeah. Okay, now the traditional view is, the theory of infinite series solved that because in the theory that you learn in your calculus classes, you can calculate the sum of the infinite series distances and it's finite. Right, so like, okay, the first distance is 1/2, the second is 1/4, the third is 1/8. And according to calculus, when you do the sum, the infinite sum of 1/2 to the n, as n goes from 1 to infinity, that's 1, it's not infinity. Okay, so if Zeno's argument was the distance must be infinite because there's an infinite number of finite distances, then Zeno would be wrong. Then he would have been refuted by that. But I don't think that was his argument. By the way, I don't know because we don't actually have Zeno's writings. We only have Aristotle's discussion of it. Okay, but his argument might have been premise. It's impossible to complete an infinite series. Okay, second premise, to get from point A to point B, you have to complete an infinite series. Conclusion, you can't get to point B.
So okay, if you are moving from point A to point B and covering a finite distance, are you still doing that by traversing an infinite number of distances? And then
Yeah.
how would you resolve that then?
Um, I mean, basically, I think that there's a kind of equivocation in the argument, right? So, okay, why can you not complete an infinite series? Okay, like, so the way that I stated the argument just now, I would say what's wrong is the first premise is false. You can complete an infinite series. Okay, and I'm going to prove it now. So I just completed an infinite series by moving my hand. Okay. Okay, why does Zeno think you can't do that? Well, so here's a sub-argument. An infinite series is a series that has no end. It's impossible to come to the end of a series that has no end. And in order to complete a series, you have to come to the end of it. Okay, so you can't complete it. Yeah, it seems logical. Okay, so now I think that involves an equivocation. Right? Okay, so completing a series might be taken to mean coming to the last member of the series. Or it might be taken to mean coming to a point in time at which every member has been done prior to that time. So if a series has no last member, it cannot be completed in the sense of getting to the last member of the series. However, also, if a series has no last member, it's not required to come to the last member in order to complete the series, right? In the sense of getting through every member, right? If it doesn't have a last member, then that's not one of the members, so you don't have to do the last member. So, right, so it's possible to do every member without doing the last member because there isn't one. Right?
So could it be resolved? And I'm just thinking here that you would never complete that infinite series, but the difference would be so small and so imperceptible that in our world, in our macro world, you would have completed it, but in reality, when you go to the atomic, subatomic, you wouldn't have completed it.
Yeah. I mean, sometimes students are tempted to say that, right? Like, oh, maybe you just get really close to the end point and you just don't notice that you didn't make it all the way. But no, that doesn't work because if the argument works to show that you don't get all the way to point B, you could just take any other point. So you use the same argument to show that you don't get to the first halfway point, right? Because in order to get there, you have to go half the distance and half the radius, right? Okay, like you can't go to any point at all, not a point that's close to the end, right?
True. Yeah. You don't believe in the calculus proof of or the resolution of this theory. So, what I was going to ask is it an example, according to the mainstream view of how mathematics can be used to solve philosophical problems?
Yeah, I think some people think that. I think Alfred North Whitehead thought that, if I'm remembering correctly. And he was a pretty important philosopher and also logician. So it's not a totally stupid thing to think, right? I think it was just sort of like, I think it's correct about one way of construing the argument. It's not correct about another way of construing the argument, right? Like the theory of infinite series resolves the confused argument that the sum has to be infinity.
Yeah. So, just to wrap my head around it one more time, what is your exact answer to Zeno's paradox? How do you resolve it?
Yeah, I mean, the short version is you can complete an infinite series.
You can.
Yeah.
You can complete it without reaching the last member of that series.
Yeah, there's not a last member, so you don't have to reach that.
Okay.
It's like, my analogy is, I'm going away for vacation. I tell you, I want you to feed all of my pets. Okay, I go away and then I come back and I say, did you feed the turtle? And you say, I didn't see any turtle. I go, yeah, I know, but did you feed him? No. Right. No, you didn't have a turtle.
Okay. So then how would you know that you've completed the series, really? Because you are going to a specific, you're still going to a specific, I know you don't like the word point, but you're going somewhere at the end. You're completing that distance.
Yeah. So, okay, well, you walk from point A to point B, you completed the infinite series.
Yeah.
You know that you did because you have eyes and you just look and you just see yourself moving.
Yeah.
Yeah.
All right. Great. And then what does it mean to say that the sum of an infinite series is one? or a specific number.
Yeah. Yeah. So, I mean, this is a good thing to point out because, like, I think a lot of students crucially misunderstand this. A lot of students think that the sum of an infinite series means the result that you get to after you add up all the infinitely many terms. And that's not what it means according to the standard analysis, right? In the standard analysis, it means there's a number that you get closer and closer to as you add more and more of the terms. And it's defined that way intentionally to avoid the idea that you could actually get to the end, right? That is, the mathematicians are specifically trying to avoid saying that you can add up infinitely many terms. They're just saying you can add up larger and larger numbers. And as you do so, you'll get closer and closer to 1 as a result. And that's what it means that the sum is 1.
Yeah.
And notice that means that the word sum has a different meaning when you're talking about infinite collections than when you're talking about a finite collection of numbers.
So to tie it back to your argument of Zeno's paradox is, if the sum of an infinite series is 1, you can reach 1, but you still haven't completed all the points in the series. You're just bypassing them?
Well, no. I mean, you don't bypass any points. You have to go through all of them.
Yeah.
You just go through all of them, and then you get to the end point, right? By the way, it's like so you go from point A to point B, right? Point B is at the end of your journey, point B. But point B is not a part of the Zeno series. The Zeno series is these halfway motions, which are all of finite size. Point B is a size 0 object, if there are such things. So that's actually not part of the series. That's why the series doesn't have an endpoint. The series doesn't have a last member, right? Although you have a final stage after you've done the series.
Right, great. Any other points you wanted to illustrate about it in terms of misconceptions about infinity, or?
Yeah, I don't know. I mean, I'm not sure if your listeners have heard all of the amazing paradoxes of the infinite. So, it's
No, can you go over like just a few of the, without, you don't have to resolve them, but just go over a few of the paradoxes that you kind of touch on in the book?
Yeah, so I mean, there's Thomson's lamp, which is kind of easy to explain. There's a lamp that let's say it starts out off, you switch it on after half a minute, and then you switch it off again after a quarter minute, then after another eighth of a minute, back on, off. Okay, so within 1 minute, it gets switched infinitely many times. At the end of the minute, is it on or off? Right? And then, so this is from James F. Thomson, and Thomson says, oh, well, like it started out off, and after that, it was never switched on without subsequently being switched back off again. So it's got to be off at the end. And then there's a parallel argument. Like you switched it on after half a minute. After that, it was never turned off without subsequently being switched back on again. So it's got to be on, right? Right. And so, and then his conclusion is that you can't perform an infinite number of actions or something like that.
Yeah.
That's one. There's let's see. There's this Archimedes paradox. Okay, so here's a version of it that's kind of interesting. Okay, so there's this slab of stone, which let's say there's a black slab of stone, which is 1/2 inch thick, and then on top of it there's a white slab that's a 1/4 inch thick. By the way, all of these are perfectly opaque. And on top of that, there's another slab, 1/8 of an inch, and so on, right? But alternating colors, but getting smaller and smaller. So the entire stack is a total of 1 inch, right? Or maybe infinitesimally less than 1 inch, because it doesn't have a top. Okay, so you have that.
It's approaching 1 inch, as you'd say.
Yeah, yeah. And so you stand over the pile and look down, and what do you see? And so it's like, well, I mean, you've got to see something, and you can't see the pile because all of the slabs are opaque. But do you see black or white, or gray or blue? Do you see some completely unrelated thing? Right? Like, you can't see any particular slab because each slab is occluded by the one on top of it.
Yep.
But then, so that's puzzling. Okay, and then there's a third one, maybe this will be enough. There's a third one that's, let's say there's there's a pile of infinitely many dollar bills, and they're labeled with natural numbers, you know, bill number 1, number 2, number 3, and so on. Like, the pile is stretching away to infinity. Okay, and then you're going to play this game, right? So, like, let's say I play this game with you, and in the first round of the game, okay, I give you bill number 1, and then I offer to trade bills 2 through 10 for bill number 1. Right? So like you give me bill 1, I give you 2 through 10. Good. And you go, okay, that sounds good. And then in the second round of the game, I say, hey, give me bill number 2. I'll give bills 11 through 20. You take that, okay. And so the game just continues this way. And imagine that, you know, it takes half a minute to do the first round game and then a quarter of a minute to do the second round of the game and an eighth of a minute, et cetera, so that we could complete the whole game in 1 minute. That appears to be a logically consistent description of something that could be done. And then the question is, at the end of the game, how much money do you have? Okay, and so, you know, there are two arguments. One argument is, oh, you should have an infinite amount of money because in each round you took a $9 net profit, right? You gave away $1 and you got 10, so $9 profit. So your total quantity at the end should be 9 times infinity, which is infinite. And then here's the second argument. You have nothing at the end because, you know, what's the lowest numbered bill that you have at the end of the game? And so there isn't one. Like,
Yeah.
So I have bill number 1 because you gave it to me in round 1. I also have bill number 2 because you gave it to me in round 2. I also have bill number 3, right? I have bill number n for each n because you gave to me in round number n. So I have all the bills, so you have 0.
Yeah. That's it's really fascinating. So you promise that if somebody reads your book from one of the listeners, that they'll be crystal clear on how to resolve these paradoxes.
Yes, I promise.
All right, great.
You'll
Awesome.
be completely persuaded, and yeah.
All right, just crystal clear, no doubt. Awesome. Great. Well, thank you very much. Thank you for taking the time for being here.
Yeah, thank you.